Hey everyone, and welcome back to another video series. In this video series, I'll be teaching you, or more like I'll be walking you through while doing it for myself, how I can implement a paper, a neural network paper using Python. Now, I have already chosen a paper. It is a neural algorithm of artistic style or neural style transfer. This is the paper that I'm going to try to implement, and I have it opened up right here. I haven't downloaded it yet, but this is it. So that's pretty much the objective of this video series. So before we actually jump right into the code and all of the paper stuff, I kind of just wanted to, I don't know, give a little bit of a disclaimer. Just I think I should give one since I haven't uploaded in quite a while. I think my last video was 2 to 3 months ago, and I know maybe some of you might be wondering if I had quit YouTube or something like that. Well, I just wanted to kind of iron out those things. Mainly it's just that I'm not quitting YouTube. I'm still gonna be uploading, but I wouldn't upload. I'm not, like I would don't expect that I'll be uploading a lot. It's definitely gonna be a lot lesser than what I used to upload. It's just that uh, I have many academic commitments that I have to meet, and it's like I have to do that, and that's currently my priority. So that's pretty much why I'm not going to be able to upload a lot. I'll still upload, but I don't know how much. So yeah, so just that's the disclaimer. All right, so let's leave all of that and let's actually start with this video. So I have opened up this archive archive thing right here, and I'll just go ahead and download the PDF. You should also do that. I'll probably have a link to this in the description down below so you guys can do it yourself. Okay, why is it taking so long? Okay, there we go. All right, so we have downloaded the file. I'll just Okay, so first off, this video really is mainly going to be dedicated to understanding the paper, maybe making a few notes according to like what's happening in the paper along the way, and that's just going to be it. In the next video, we'll actually jump into the code and we'll kind of implement something. So that's kind of the way I'm trying to segregate these two videos, is to just focus on one thing at one point. So you can see this is the paper right here. It is 16 pages long. Although I have looked at this paper before, just like that, and as far as I remember, a lot of it is just results. So the actual content isn't that much. So I'm just gonna go over to my desktop. I'm gonna make a new folder, neural style transfer transfer. I'm gonna create that and I'm gonna save it right in there. Alright, now that that's done, we can just close this, and I'm also gonna go out of here, and I am gonna open this with preview. Alright, perfect. So now we can actually get started with understanding what this paper is and all of that fun stuff. Alright, so as you can see, 16 pages long. Let's just take a quick look at the paper and you will see that the last many pages is just references. The last 3 pages is just references. This is all actual content, and then we have a bunch of these results pages where they kind of just show you what the results are according to like certain parameters that they have altered, stuff like that. As you can see, it looks pretty beautiful. Now, first of all, I think I just want to explain to you in just normal words what this thing is trying to achieve. I think that's something that I want to do. And I think that, because the thing is, a lot of the times these papers, they dive into a lot of the mathematics, but they don't look at the intuition. Like, what I mean is, they pretty much assume that everyone understands that, and then they just directly dive into the math. For example, if you look at the GAN paper, the original GAN paper, it was extremely mathematically complex. And I just thought that it wasn't that well written for someone who is kind of a beginner in that area. I mean, as opposed to that, if you look at the conditional CAN paper, it was really well written for that matter. So that's just something that I wanted to say. All right, so I'm gonna just explain to you with a just gonna give you a very very basic understanding of what neural style transfer is, so you know what it is that we are trying to do, and so if I do certain things, then you at least know why that's the case. All right, so that's kind of my goal for the first few minutes, is just to give you that idea. So I'm just gonna quickly share my screen so you guys can kind of see what's happening. Just give me a second. I just have to mirror my display. All right, I think that's done. It should take a second or two. There we go. Okay. All right. Okay. So the first thing we have to do is understand what neural style transfer is. So I'm just gonna choose a different color. What is neural style transfer? I hope you guys are able to comprehend what I'm writing. I mean, I am writing with the Apple Pencil, but I mean, my writing is still not that great. So yeah. All right. So what is neural style transfer? So basically, it is a form of it's based on images which you could have seen from the paper itself. But basically, in neural style transfer, we usually use like a pre-trained model. At least that's what the paper used, and that's what I've seen in like most implementations. You use the model which is the VGG. You use the VGG, I think 19. I think that's the model everyone uses. We'll see it in the paper. And the way you do it is you have two images that you feed into your network. So you can have these two images. The first image that you have is known as the content image, and then this is going to be your style image. Now, as the names kind of sort of suggest, the content image is generally just going to be some actual image that you like, or maybe some sort of a painting or something like that. So just assume that this is like, let's say, the Mona Lisa, something like that. And then the style image is some other thing, just something else. Maybe let's say that the style image is some abstract art. I mean, abstract art is really just a bunch of wavy lines. So I'm just gonna draw that. So let's say that this is your style image. Now the goal of neural style transfer is to take this style image and take these content images. You want to take these two and you want to produce another image which is going to be like your output image or your result image. What it will do is it will basically have your character, your main character in there, but it will also have these wavy lines, and they will be a part of the character, but it will be like the character will still be there. So this is kind of what you are assuming. So this is going to be your result. So that is really just the goal of neural style transfer. You can see through my very well annotated, drawn out example how it works. So this is pretty much how it is, and this is pretty much how it works. So now that we have a very basic, superficial understanding of how all of this works, and I really like the one with the tail. But yeah. Alright, that was a detour. But alright. So now that we have a superficial understanding of how this works, we can actually jump into the paper itself and actually understand the intricacies. Because I mean, from what I have shown you right now, you can see that it's fairly superficial. But if you actually look at it, like it is fairly difficult to implement. I mean, I'm not gonna say it's extremely difficult, but it is kind of difficult to implement. All right, so this is the paper, neural algorithm of artistic style. Perfect. So this is just the abstract kind of thing. I mean, they haven't actually written anything, but whatever. So here they just say, in fine art, especially painting, humans have mastered the skill to create unique visual experiences through blah 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 blah. I don't really want to do that. So you can see thus far the algorithmic basis of this process is unknown, and there is no artificial system with similar capabilities. However, in other areas of visual perception, such as object and face recognition, near human performance was recently demonstrated by deep neural nets. I mean, this paper is fairly new. Like it's not too new, but still. I don't know why they have written it like that. It feels like they were just discovered like 2 days ago, something like that. All right. The class of deep neural networks that are most powerful with image processing tasks are called convolutional neural networks, which obviously makes sense. Convolutional neural networks consist of layers of small computational units that process visual information hierarchically in a feed-forward manner. Now, this all sounds really like mind-boggling complex. Really, all they are trying to say. I mean, this is the problem with these papers. The way they are written out, I mean, it's like they have written some crazy stuff, and you need like some like dictionary and something like that to decode what they are written. But this is for the people who don't exactly understood what was written in in this area. This is just a small example of what you can expect from the paper. All they are saying is that the way convolutional nets work, or more like the way a convolutional layer works, is that rather than being a normal feed forward where it basically just takes in the entire like the outputs of the entire previous layer as an input, to each neuron, it just takes its own receptive field rather than the whole thing. So it's not a fully like it is not a fully connected neural network. It's more like a partially connected neural network. But the reason why it said feed forward is because, I mean, you're pretty much still doing the same thing. It's just that you are having it just with that single receptive field, which is your small computational unit. So you can see why, I mean, I think that it might not be the best idea for a total beginner to read papers like this. I mean, they'll just be extremely, I would say, uh, just, I mean, it would just be overwhelming because they'll be thrown with all of this information that's really super simple, but it's framed in such a complex way. All right, so that's a I'm going off on tangents here. All right, each layer of units can be understood like image filters, each that extracts a certain feature from the input image. This is kind of an important thing because this is one of the bases of neural style transfer. So then you get these feature maps. All right. Okay, now this is I think gonna be an important thing. So when convolutional neural networks are trained on object recognition, they develop a representation of the image that makes object information increasingly explicit along the process hierarchy. All this says is that as and when you have more and more convolutions, your ability to detect macro patterns, and more like, actually not macro patterns, more like micro patterns, gets better and better. So basically, if you have an image of a lion and you just pass it through one or two convolutions, then it will just get some basic macro patterns in that image. Maybe just some very basic things like just the basic shape of the body, things like that. But if you actually pass it through several different convolutions, I mean, maybe it will get like the positions of the eyes, then maybe the position of the whiskers, something like that, which it wouldn't be able to get otherwise. And that's pretty much what they're saying, is that if they have several different convolutions, then that should get better. So higher layers in the network capture high level content in terms of objects and their arrangement in the input image, but do not constrain the exact pixel values of the reconstruction. That's exactly what I was trying to say. So in contrast, reconstructions from lower layers simply reproduce the exact pixel values of the image. We therefore refer to the feature responses in higher layer as content representations. We should keep this because content representation is kind of an important term. To obtain a representation of the style of an input image, we use a feature space originally designed to capture texture information. This feature space is built on top of feature responses in each layer of the network. It consists of the correlations between different feature responses over the spatial extent of the feature maps. I'm not going to check this right now. By including the feature correlations of multiple layers, we obtain a stationary multi-scale representation of the input image with its texture information, but not the global arrangement. I'm not. I mean, if this is kind of what it is trying to say. No, this is for the content representations. This is not for the. Basically, I mean, kind of what they're trying to say is that uh, the way this works really is. I mean, if you read through this, this is written in a very complex way, and frankly, even I am having a bit of a hard time explaining what it is that this is doing. really all they are saying is they are using, like, they're pretty much doing the exact same thing. All they are doing is they are just capturing the outputs given by the various filters, and since each of those filters is giving you a unique kind of a representation or some unique thing about the image, they are just using that. And then slowly and over time, that initially you just start with that small thing, and then slowly and slowly it will go up. So that's kind of what they are doing. So this is your thing. So a convolution, a given input image is a set of filtered images at each processing stage of the CNN. While the number of different filters increases along the processing hierarchy, the size of the filtered images is reduced by some downsampling mechanism. Example, max pooling. We can use that. Leading to a decrease in total number of units per layer of the network. Content reconstruction. We can visualize the information at the different processing stage of in the CNN by reconstructing the input image from only knowing the network responses in a particular layer. We reconstruct the input image from layers con1, 1a, and all of these of the original VGG network, which is exactly what I was talking to you about. So yeah, we find the reconstruction from the lower layers almost perfect. In higher layers of the network, detailed pixel information is lost, which is exactly what I was trying to tell you. And while the high level content of the image is preserved in the D and E style reconstructions. Alright. On top of the original CNN representations, we build a new feature space that captures the style of an input image. The style representation computes correlations between different features in different layers of the CNN. I think this is kind of sort of fairly understood if you understand like statistics and basic math. Often like that goes inside neural nets. I So like, because if I try to explain this right now, this might take a little while, so I'm not gonna really dive into this since this is a little bit more mathematical. So I highly recommend you understand what these terms mean. I mean, if you understand what this means, then you pretty much understood the entire line. All right. So we reconstruct the style of the input image from style representations built on different subsets of CNN layers. So these, I'm pretty sure, are the style layers. So we'll do that. Again, we can visualize the information captured by these style feature spaces built on different layers of the network by reconstructing an image that matches the style representation. Uh, Indeed, reconstructions from the style features produce texturized versions of the input image that capture the general appearance in terms of the color and localized structure. Moreover, the style and complexity of local images structures in the input image increases along the hierarchy, a result that can be explained by increasing receptive sizes and feature complexity. Not that important, I would say. Alright, so the images are synthesized. Alright, let's see. Irrespective of the respective art piece, while the global arrangement. Alright, so this stuff is just boilerplate, exactly like all of those very tiny details that about how it works. Frankly, I don't really want to read this. To be honest, you don't really need to read this. You should, but I'm not gonna. I mean, maybe I might regret this later on, but for now, I'm not gonna. Alright, so this is kind of some of the results that you can get. Yeah, they look pretty good. I would definitely say that. But yeah, I really like maybe this one. But yeah, I mean, you can definitely let me know. Whatever. Alright. So you can see that this says that of course image content and style cannot be completely entangled. While synthesizing an image that combines the content of one image with the style of other, there usually does not exist an image that perfectly matches both constraints at the same time. However, the loss function we minimize during the image synthesis consists of two terms for content and style respectively. There we go. So this means that your network has two loss functions, which should kind of sort of be obvious almost, but that's alright. We can therefore smoothly regulate the emphasis on either reconstructing the content or the style. A strong emphasis on the style will result in images that match the appearance of the artwork, effectively giving a texturized version of it, but hardly shows any of the photograph's content. And placing strong emphasis on the content, one can clearly identify the photograph, but the style of the painting is not well matched. Here they present an ANN that achieves a separation of content from the style. So this is it. So now if we go into the method section, this is the main section. This is like the meat of the actual, I would say, paper. And you can see there are a few equations here. So if you are scared of math, don't really worry. I'll kind of walk you through what this stuff means. So I don't think this should be too overwhelming. Alright, so the results presented in the main text were generally on the basis of the VGG network, a convolutional network that rivals human performance on a visual object recognition benchmark test, and was introduced and extensively described in. We used the feature space provided by the 16 convolutions and 5 pooling layers of the 19-layer VGG network. We do not use any fully connected layers. This model is publicly blah blah blah. Generally, each layer in the network defines a non-linear filter bank whose complexity increases with the position of the layer in the neural network. Hence, the given input image X is encoded in each layer of the CNN by the filter responses to that image. Pretty basic stuff. That's kind of how the CNN works. Earlier, with N1 distinct filters, has NL different feature maps of size ML. Now, this is something that these are the notations that you should kind of keep in mind because they will be using it, and if you don't know what that word means, well then in the equation, then you can't really implement that equation. So where ml is the height times the width of this feature map, so it's kind of like just a size. So the responses in the layer L can be stored in a matrix FL, where FL is a set of real numbers. It's a matrix of real numbers of size NL by ML, where FIL sub ij is the activation of the ith filter at the position j in layer L. To visualize the image information that is encoded, figure 1, we perform gradient descent on a white noise to find another image that matches the feature responses of the original image. So let P and X be the original image that is generated, PL and FL be respective feature representations in layer L. We then define the squared error loss between the two representations. So this is kind of what is happening over here. We can just kind of do that. The derivative of the loss with respect to the activations in layer L equals this. Okay, so I'm guessing we have used ReLU. And to be honest, you don't really need to understand what this is. This is handled by your deep learning libraries. Whatever it is using, whatever you're using, PyTorch, TensorFlow, whatever. I am pretty sure they're talking about ReLU over here. I've seen ReLU's derivative and it's very similar to this, so that's why. But whatever. So yeah. Again, you don't need to understand what this is. This is calculus. If you don't know calculus, it's okay. From which the gradient with respect to the x can be computed by using standard error backpropagation. Thus, we can initially change random image x until it generates the same response in a certain layer of the original image p. And yeah, they did say that. On top of the CNN responses in each layer, we build a style representation that computes correlation. Why are they repeating the same things? These feature correlations are given by the Gram matrix, this, where Gij is the inner product between the vectorized feature map in the I and j layer. And that's your equation right there. To generate a texture that matches the style of a given image, we use gradient descent from a white noise image to find another image that matches the style representation of the original image. This is done by minimizing the mean square distance between the entries of the Gram matrix from the original image and the Gram matrix of the image to be generated. So this is your loss function right here. So let A and X be the original image and the image that is generated, and AL and GL be the respective style representations in layer L. So here you have your total loss, and then you have this where W1 is the weighting factor of the contribution of each layer to the total loss. So we can just highlight these two things. Alright, the gradients of EL with respect to the can be readily computed using blah blah blah, all of that we know. Alright, so the total loss can be written like this, and that's it. That is the paper right here. As you can see, I have underlined, highlighted all of the important parts of this paper, and I would recommend that, if you haven't done what I have done over here, like underlining and stuff, it is a good practice. I was kind of hoping that you would have picked it up along, like while I was doing it myself. uh, I mean, other than that, really, there isn't a lot to mention. I mean, we might get into a few more intricacies when we are actually writing out the code. But for now, I don't think there is any real additional information that I can give regarding the paper. I would recommend that you give it a shot. You try to implement it yourself. And before I even start doing this myself, what I'm gonna do is I'm gonna show you a few I'm gonna show you some code that pretty much does the same thing. It is on towards data science. There's a chance I might use a lot of code from this, so I just thought I'd kind of mention it. Main reason being, I want you to try to do this yourself. I'm gonna be making the next video, but I just want you to do it yourself. So you can see that they have this entire code. It's written in PyTorch, which is what I'm gonna be using. So yeah, you can see that they already have written a lot of the code for this, and it's written really nicely, I would definitely say. So yeah, that's pretty cool. All right, whatever. So that's it for